Hi guys, Dr. Hasbullah here, and in this video we're going to continue our discussion about Mach number, and specifically what we are going to be looking at is the relationship between area changes and also velocity. So before we studied compressible flow, we are already very familiar with incompressible flow. So in incompressible flow, we know that when area increases, velocity will go down, right? And when area decreases, the velocity will go up. In this video, it's going to be quite interesting because at supersonic flow, which is Mach number greater than 1, you're going to see that when the area increase, velocity will also increase, and when the area decrease, velocity will also decrease. Okay, so we are already very familiar with this equation, which is m dot equal to rho times velocity times area. Okay, meaning that in steady flow, rho 1 times V1 times A1 equal to rho 2 times V2 times A2. And for incompressible flow, the density at point 1 will be similar with velocity at point 2, so I can cancel this out. And what's left is V1 A1 equal to V2 A2. So this is for incompressible flow. And it is very clear that in this relationship that when velocity goes up, okay, the area will go down. So basically, if you want to increase the velocity of a flow in pipe, for example, you're going to make the diameter of the pipe smaller. Alright, in that way, you will get higher velocity at the same mass flow rate. Alright, and for compressible flow, let's take a look at the relationship. So compressible flow, if you have a pipe that's changing in area, okay, and now you have the inlet, okay, this is your control volume. Alright, so this is your inlet, and this is your outlet, right? So for inlet, let's say that the density is rho, the velocity is v, and the area is a. Okay, but at the exit, then this is going to be rho plus d rho, v plus dv, and area plus d area. Okay, so everything has changed because this is compressible. So rho will change slightly, so that is d rho. Velocity will change slightly, and area will also change slightly. So now let's go back to this relationship, and this is point 1 and this is point 2. Okay, if the equation says rho 1 V1 A1 equal to rho 2 V2 A2, now I'm going to have rho times velocity times area, this is at point number 1, okay, equal to rho plus d rho times v plus dv times a plus dA. Alright, so this is at point 1. Okay, and this is at point 2. Alright, and now let's see where this equation takes us, right? Let's try to solve the right hand side. Okay, this is obviously rho times v times a plus rho times v times dA plus rho times dv times a plus rho times dv times dA plus d rho times v times a plus d rho times v times dA plus rho times dv times a plus, sorry, this is d rho times dv times a plus d rho times dv times dA. Okay, so as usual, if you have two changes, right, dv times dA, you're going to cancel it out because the multiplication result of these two d's will be very small that you can neglect it. Okay, so you'll end up with a few equations. So this cannot be cancelled, this cannot be cancelled, this is staying, this can be cancelled, this is staying, and this can be cancelled, this can cancel, and this can also be cancelled. So you will end up with, this is rho times velocity times area plus rho v dA plus rho A dV plus VA d rho. Okay, and these two can be cancelled out, okay, because you have rho VA on the left and on the right. So you will end up with rho V dA plus rho A dV plus VA d rho equal to 0. Okay, and if I divide everything with 1 over rho VA, okay, let's see what happens. So this will be dA over A plus dV over V plus d rho over rho equal to 0. Alright, and we were saying before that we want to find the relationship between velocity and area, right? Okay, and now we have here area and we have velocity, but we also have rho. Okay, and let's see what we can do about this rho so that we can obtain the relationship between velocity and area. Now let's go back to a concept that you have already learned before, which is called Bernoulli Equation. And Bernoulli Equation says that P over rho G plus V square over 2G plus H equal to constant. Okay, so if you have point 1 on the left, the total of P over rho G plus V square over 2G plus H at 1 will equal to the total of that at point 2. Alright, so now let's assume that the pipe is a horizontal pipe, so H will be eliminated. And I want P as the title, so this is going to be P plus rho V square over 2 equal to constant. Okay, can I do that? Alright, so now P is equal to C minus rho V square over 2. Right, let's carry on. And what I want here is dP over dV. So dP over dV equal to, now constant is now 0. So this is negative 2 rho V over 2. And you will end up with dP over dV equal to minus rho V. And if I move dV to the right, you will get dP equal to minus rho V dV. Okay, and if I want to divide everything with d rho, okay, and I want to divide everything with d rho, okay, d rho, so you will end up with dP over d rho equal to minus rho V dV over d rho. So here you need to be careful. So just make sure that you recognize well which one is P and which one is rho. Do not mix those two together. Okay, and dP over d rho is actually something that we have found before. Okay, let's take a look where it is. Okay, and if you remember this, okay, C is actually square root of dP over d rho. Okay, so dP over d rho itself is actually C square. And what is C? C is the speed of sound. Alright, let's write it there. So this will be C square equal to minus rho over d rho times V dV. Okay, and we are also looking for the replacement of d rho over rho. Okay, and this is a suitable replacement to put here. Okay, so now we are looking for d rho over rho. So d rho, let's do this in black. Okay, so d rho over rho is equal to minus V dV over C square. Okay, and this is quite an important relationship, and I'm just going to write this equation again here at the bottom. So dA over A plus dV over V plus d rho over rho equal to 0. And now I want to replace d rho over rho with this equation, right? And you will end up with dA over A plus dV over V minus V dV over C square equal to 0. Okay, and what I want to do now is to have this equation and multiply this with V over V. Okay, you'll see later why. And this means I will end up with dA over A plus dV over V minus V square over C square dV over V. This is equal to 0. And the reason why I wanted to have here V over V is so that I can get V square over C square here. And if you remember, Mach number is equal to velocity divided by speed of sound. So this is clearly m square, right? So this is clearly m square. And if I take A to the right and V to the left, I will end up with dV over V m square minus 1 equal to dA over A. Okay, and this is the important equation that we were looking for. Okay, and in discussing compressible flow, this relationship is very important. This relationship shows how area change with velocity, or how velocity change with area. And now let's take a minute to understand what this equation tells you. Okay, let's have two cases, right? So this is, on the left is Mach number less than 1. This is Mach number greater than 1. Okay, so obviously this is subsonic flow. And this is clearly supersonic flow. Okay, and when Mach number is less than 1, okay, and you plug it here, okay, and you plug it here, right? Now, let's see. When Mach number is less than 1, you will have minus dV over V times something, right, equal to dA over A. This means that when you increase the area, okay, the velocity will go down. Okay, typical, right? This is normal. So when you reduce the area, velocity will go up. This is quite normal, okay? We see this every day, okay? That is why we pinch the hose, right? So that we can water the plant further away. It's just to make the area smaller so that the velocity will go higher and the water can go further, right? And now, let's see something a little bit different, which is when Mach number is greater than 1. Okay, so what happens when Mach number is greater than 1? Okay, so this here, this term will be positive, alright? So dV over V multiply with whatever number it is equal to dA over A. Alright, and because both left and right hand side is positive, right? When area increase, right, the velocity will also increase. Now, if you think about it, this is quite counterintuitive, right? So when you have a diverging duct, right, you expect the velocity to be slower at the end, right? But if the Mach number is greater than 1, if the flow is supersonic, right, and you have the duct that is going larger and larger, the velocity will actually increase. Okay, now this I think is quite interesting and it is quite counterintuitive. And similarly, if the area goes down, the velocity will also goes down. Okay, and what is the implication of this? Now, let's say you want to increase the velocity from subsonic to supersonic. Okay, what do? Alright, so when the flow is subsonic, you know that to increase the velocity, you have to reduce the area. Okay, so what you do is you reduce the area. Okay, you reduce the area. If you keep reducing the area, the velocity will continue to increase, right? Until Mach number equal to 1. Okay, and then to increase the Mach number further, let's say to increase it to Mach number 2, then this follows this relationship. Okay, you cannot continue to reduce the size of the pipe because the velocity will go down now. right? Because the flow is now supersonic. So what you do is, after the Mach number reaches 1 here, okay, you increase the flow area, okay, and in here you will have Mach number greater than 1. Okay, so the flow is moving from left to right. Here is obviously Mach number less than 1. Okay, and at the transition region, okay, in here, okay, at this region, okay, at this region, the area change is actually 0, isn't it? Okay, because the area doesn't change anymore. Okay, it goes from smallest to higher value of area. So the transition is actually meaning that area change is 0. So dA here is 0. Okay, now let's take a look at this equation. What happens if dA equal to 0? Okay, you will end up with Mach number square minus 1 equal to 0. So Mach number is actually 1. Okay, that is why Mach number will only equal to 1 at the throat region. Okay, this is what you call throat area. Throat area. Okay, so supersonic flow can only occur when you have throat. Okay, so the flow goes smaller and it goes bigger. And this is the reason why supersonic flight, okay, the nozzle at the back of the flight is diverging, right? It's not converging. Okay, it has to diverge because the velocity will continue to increase when the flow area is increasing. Okay, so this is a new concept for you, and I think this is all for today. Thank you very much, and I'll talk to you soon. Bye.